For direct comparison, I'm going to give you a little bit of a backstory so it'll make sense of what's going on as we do this. Let's say I have on a graph a series that seems to be decreasing or is actually decreasing. Now it's going to be a list of terms, so to draw it as connected is a little bit misleading, but this will work for the moment. What you're going to do is if you think it's going to decrease and then what you want to but you don't have, it's not one of your basic ones, then you can do a direct comparison. And what the direct comparison means is you're going to compare it with one that you know is decreasing. Because if this one, the red one, is a known, if it's known, oops, that's a little bit of thick writing, I'm sorry about that, to converge, and it is bigger than the one that you are trying to figure out. So this one is bigger than the one you're trying to figure out, and we know this red one converges, that one's known, then by default, or by logic, this brown one also converges. So that is the way the first one works. However, we have the same scenario, and I'm going to draw basically beg your pardon, I meant to write it in brown. I'm going to draw a very similar graph. And this one, the series seems to be diverging. We don't actually know, but that's what it appears to be. Well, if my known series is smaller and does diverge, what that actually means, and I'm going to write it again, this one is known. Maybe it's known. Maybe it's a p-series, maybe it's a geometric. It could be any number of things. You could do integral, you could do even an nth term test. But if it is known to diverge, and it is smaller, that's a diverge, and it is smaller than the one I'm looking for, then if my known one diverges, then logic will tell us that the one we're trying to prove also diverges. The problem is if I have one that fits right in here. If this one diverges, and it's known to diverge, but it's bigger than the one I'm looking for, we have no guarantees because we know this one's going to take off and diverge, but that doesn't mean this one here will also diverge because it could come and converge. So you have to be really careful that if you're diverging, you need a smaller series, and if you're converging, you need a bigger series. So you kind of have to take it, I call it take it with you. You have to take a converging one down with you to smaller, and you have to take a larger diverging one up with you so that they both follow up. So that's what this one is about. I'm going to put some examples on the next one. Here is my series. It could work if you've already seen limit comparison test. You could compare it to 1 over n cubed, and you could do the limit comparison test, and that would also work. But since we're talking about direct comparison, I want to show it to you. The one I'm picking by p series does converge. So since it goes down and it converges, I need this one that I am picking, this one to be larger. So the way I show that, or equal to. So when I do a comparison, what I usually do in my head, or what I do first, is I plug in the very first number that's given here, and I just plug in a couple numbers to see if I can kind of prove it to myself. The one when I plug in 1, I get 1 over 1 cubed plus 1, so it would be 1 plus 1, which is 2, and that is smaller than 1 over 1, because that's a half. So when I plug in 2, I have 1 over 2 cubed is 8 plus 1, which is smaller than 1 over 8. And what that shows me, plugging in a few numbers, is that this one here will always be smaller because it's the same denominator plus 1, and when your denominator grows, it makes the whole thing smaller. So by logic, or by mathematical, I know that n3 plus 1 is smaller or equal to 1 over n to the third. Because I know this, then I can say the series I have then does converge as well. So my series, and this is how you would write it to infinity, n equals 1 to infinity, of 1 over n 3 plus 1 converges by direct comparison. The things you're going to need to show with this one is you need to show what you need to show what you're comparing it to. You need to show this comparison to say that it is smaller, and then your conclusion. So there's 3 parts to this that you need to show. Let's head on to a second example. My second example is going to be very similar to this one we just did. Example 2 is n equals 1 to infinity. However, the denominator is going to look a little bit different. This is 3 to the n plus 2. That is not a straight up geometric, but I can compare it to the geometric one. That would be 3 to the n. By geometric, this series converges. I'm sorry, I lost my pen there for a moment. Converges. And because it converges, then I now need to, and that'd be n equals 1 to infinity. Now I need to do a comparison, and my comparison is 3 to the n, and that's a plus 2. Is that smaller or equal to 1 over 3 to the n? And you can plug in some numbers mentally, but the same very similar thing is going to occur where the left side will always have a little bit more added to it in the denominator, which will then make it smaller. So this is a true statement. And so then what we can say is by direct comparison, my series, the one I'm trying to figure out, n equals 1, 1 over 3 n plus, to the n plus 2 also converges.